Okay, good afternoon, everyone. So it is our honor to invite the Professor Kim Sungwoon from Jeju National University. So he has a PhD and in kiosk, and so his topic for today is structural stability of at zero group actions. So let's welcome.
Thank you for inviting the great place, the OSEC. So today I'm gonna talk about the stability of some group actions. So my background is the hyperbolic geometry. So I moved to some space, some symmetric space, so associated to some symmetrical regroup. So and also my concern is to find some space of geometric structures, so corresponding to some discrete groups. So this stability is related to such as the area. Okay, so this work is joint work with Misha Kapovich and Jeju. Okay, so here is a cell. So throughout my talk, the X is going to be a topological space, and the gamma is a finite generated group acting on X. So by the homeomorphism of X. Okay, just you think of some, there is just some group homomorphism of gamma into the homeomorphism group of X. Okay, and you can topologize the group action on X by using some fixed generator of the gamma, and then you can easily know that the rho prime, the another action, is so close to the original action. So in terms of the generators, so in other words, the generators are close to each other, then the two actions are close to each other. Okay, so then usually the gamma is a subgroup homeomorphism of X. Okay, so usually so rho is just the inclusion map. Then there is might be no injective deformation of the original gamma action. So in this case, we say that the group action is the region. Okay, there are no deformation of the action. So then this is the main questions of our study. So which group actions are stable in some sense? So in many sense, you can talk about the stability, but here the stability means that if you perturb a little the gamma action, then you obtain some representation, right? So that all such a representation is injective, then we say that the gamma action on X is stable. So actually, you can think of the space of the all homomorphism of the gamma into the homeomorphism of X. Then there is some just inclusion homomorphism of gamma, okay, into the homeomorphism of X. Then you can think of the neighborhood of the representation. So in other words, the stable means that there exists some open subset in the homeomorphism space. So the all representation in the neighborhood of the inclusion homomorphism are injective. So that is what the stability means. Okay. So this is this stability quite happens in study of geometry structure. So usually if you have some compact GX structure on some topological compact manifold, then you can have the same GX structure around the given GX structure. So usually the GX structure are stable things. Okay, so main question is characterize all stable gamma actions on X. So this is a motivated theorem. The 1985, the Sullivan proved that. I mean, actually, the answer to this question. So when some group, so what is the stable group in? I mean, in the PSL2C. Okay. So he answered that a stable group, the stable subgroup of PSL2C is either rigid or it is the convex co-compact group. Okay. So I will give you the definition of the convex co-compact group. But anyway, so convex co-compact group, as you see the name, so it is some geometry, the things, right? But so injective, the stableness defined by some injectiveness of the representation, I mean homomorphism. So algebraic property so corresponding to some geometric property. Okay. So this is all, and also he proved that. So this is the only stable discrete subgroup of PSL2C. Okay. And also, actually, he proved that the convex co-compact group action on S2. S2 is you can think of the ideal boundary of the hyperbolic 3 space. So then, so this action is stable in the diffeomorphism of S2 as well as PSL2C. Okay. So that means that if you have some convex co-compact action on the hyperbolic 3 space, then you can think of the action as the action on the 2 sphere. And also you can perturb a little the action in diffeomorphism group of S2, then you still have an injective homomorphism. Okay, so let me start with some simple the example. Here is the hyperbolic surface, the group action. So by using some discrete group of PSL 2R, you can find some discrete group gives rise to some hyperbolic surface, okay, like this. And also, if you have the hyperbolic surface group action, then if you perturb a little, then you again get the hyperbolic structure. I mean the hyperbolic surface, the group action. So this is the basic example. So which is stable. Okay, so this is a general argument for the hyperbolic surface. So sigma G be a surface of genus G, and so gamma Z is the fundamental group. Then you can think of the all injective gamma G action on the hyperbolic 2 plane, okay, of the conjugation. Then so it is well known that this is a Teichmann space corresponding to the surface. And this Teichmann space is can think of some subset of the homomorph. So we call this character variety. So a subset of character variety. So indeed, the Teichmann space is a connected component of character variety, and also the Teichmann space is homomorphic to some RF. This is very interesting because that means that the Teichmann space consists of all the discrete and the injective the homomorphism of the surface, the fundamental group. So this is okay. So Teichmann space is the only non-rigid case among all the co-compact lattice in semi-simple ring groups, because just so you can imagine the semi-simple ring group size just a PGR. Okay. So because due to the Marcel rigidity theorem and the Magnus super rigidity theorem, so there is no deformation. So all the co-compact lattice in semi-simple ring group is rigid, except for the PSL2C case, PSL2R case. Okay. So So this is the only case, the stable case. So in semi-simple regroup case. So the surface group action is one of the most interesting object in the study of the group action. So I think that without if we don't have a surface group, then maybe the many mathematicians lose job. So surface group gives a lot of some research the object to the mathematics. Okay, so okay, so why this phenomenon happens? So this is one can explain why this kind of stability happens only in a surface group. Actually, the hyperbolicity in surface group does explain this phenomenon. Okay, so at least the genus two, there is a co-compact sigma G action on H2. Then the Miller-Savant lemma tells you that the sigma G is co-isometric to the hyperbolic 2 plane. Okay, but this one, the hyperbolic 2 plane has a negative curve geometry. So the inside the surface group, it has some kind of negative curve geometry. So this idea, the group generalized this idea. He introduced the notion of the hyperbolicity in group in 1987. So generalizing hyperbolicity in the surface group. So write this. Okay. So this is a calligraph. So given a finally generate the group, then you can get some group as the graph, so-called the calligraph. So given a group gamma, and you choose some symmetric generate set X, then you can define a calligraph like this. The vertex set consists of just the gamma, and also the edge, right, defined by like this. Then you can get out the graph. Actually, the metric space by putting the ranks 1 to each edge. Okay. So for example, for the rank 2 free group, you can with the 4 generators, then you can obtain the calligraph that looks like this. Okay. So what is the water hyperbolic group? How to know the hyperbolicity in group? So this is idea, the group idea. He first defined the delta hyperbolic space. So proper rank the space X is called the delta hyperbolic. So every triangle is a delta thing. Okay. So in space X, you draw any triangle with the geodesic side, then every triangle satisfying this condition. So you can just integrate understand what happens in triangle by this picture. So this is a delta thin triangle. So if you draw the triangle in the hyperbolic 2 plane, then triangle looks like this, right? So it is a generalization of the hyperbolicity in the hyperbolic 2 plane. Okay, so then what is the water hyperbolic group? So gamma is a water hyperbolic group if the calligraph is a delta hyperbolic space. So that means that actually the water hyperbolic group acts on the calligraph delta hyperbolic space co-compactly. So this is a kind of generalization of the compact surface group action on hyperbolic 2 plane. Okay, here, so this is the example which is not the co-compact, but you can. So this is a patch, just patch, the hyperbolic patch. But you can find some compact subset of H2, on which the group acts co-compactly. So this is also an example of stable group actions. Okay. Okay, so what is the other the stable group action? So this is this example so far the very classical the examples. So and we can see this example in many aspects of the geometry and topology and so on. Here on H3, you can get some surface group actions by embedding the hyperbolic 2 plane into the hyperbolic 3 space, like this. So then you can extend the surface group action on H2 to the hyperbolic 3 space. So we call this kind of action the function group. Okay. So function group is nothing but just the inclusion of PSL2C into the PSL2R into PSL2C. So if you have some surface group in the PSL2C, you can embed it into the PSL2C. Okay, naturally. So then, the H2 is invariant under this group action, surface group action, and so the gray circle also is a invariant under this group action. So then what happens? Then this action also stays. So that means that if you perturb this function group action, then you still have an injective injective homomorphism. So this is non-compact case. Okay, so all the hyperbolic group actions presented so far have a stability. But this is the key questions. Which property gives rise to the stability of the hyperbolic surface actions? You can do this by using some GF structure on compact manifold, but so this example cannot be explained by the GF structure. So there is some unifying notion to explain this phenomenon. So called the convex co-compact group action. This is also the very classical the object in the study of the hyperbolic three-manifold theory. So it's the stability of all the examples so far, so understood by the notion of the convex co-compact group action. So what is the convex co-compact group action? So if you have the gamma action on H3, so for that action, there exists the convex subset of H3, so on which the group action is co-compact. Okay, so this picture gives us some idea of the convex co-compact group action. So this is a kind of circle, the homeomorphic to a circle. Then actually this is a deformation of the function group action. If you start with the function group action, if you perturb a little the bigenerator, then you can get this kind of group action. But there exists some convex subset. Actually, the convex subset constructed by just the convex hull of the green line. Okay. So green line is actually we call the limit set. So this is defined by the accumulation, the point of the gamma orbit. Okay. Okay. So convex co-compact group action can be defined by many ways actually. So the first definition is just using the convex domain. But there are many equivalent conditions for convex co-compact group action. So what is the essential property for stability? So first, the existence of the convex domain, okay, by definition. So you can prove that by using the existence of convex domain on which the group action is co-compact, then you can prove the stability, it's a stability. And also the quasi-isometric embeddingness of the oblique map. So because the gamma action on this convex set is co-compact. So by the mirror summon lemma, the oblique map is a quasi-isometric embedding. Okay. So the quasi-isometric embeddingness of the oblique map is also the key property in the stability. The third, the embedding of the boundary of water hyperbolic group gamma. So what is the embedding of the boundary? So if you have a water hyperbolic group, then so it's a Kelly graph is a delta hyperbolic, right? So then you can define the ideal boundary of delta hyperbolic space because it has a negative curve geometry. And also that the boundary is well defined up to the choice of the generators. Right? Because if you define the Kelly graph, then you have to choose the generator Z, right? So depending on the generator Z, the Kelly graph is different, but the boundary is not different. Okay, so up to choosing the generator Z, the boundary of the Kelly graph is homomorphic to each other. Okay, so that means that the boundary is well defined. So this is only the property for delta hyperbolic space. So if you move to the cat zero space, then this is not true. Okay. So anyway, given the water hyperbolic group, then the boundary is well defined. Then as you see the green line, actually it's a green line. Green thing is the boundary of the water hyperbolic. Okay, so water hyperbolic group is its boundary is embedded into some boundary of the H3. Okay, so the embedding is of the boundary gives also stability. So by using one of the three conditions, you can see the stability of convex co-compact groups. Okay. And also, so that means that for all the sufficiently small perturbation of the convex co-compact group action, then you still have the injective the homomorphism. Furthermore, every injective homomorphism around the convex co-compact, the group action is again the convex co-compact group action. Okay. So it preserves some geometric property. Okay. Okay, this theorem gives you some why the boundary of water hyperbolic group is important. So Baldwin gave us some topological characterization of the water hyperbolic groups. So that means that here, so M is some compact subset, and so gamma acts on the homomorphism on M, and this action satisfies this thing. So this is a completely topological condition. Then the gamma is water hyperbolic, and also this M is a homomorphic to the boundary of the water hyperbolic gamma. Okay. So by using just the action on the boundary, you can characterize the water hyperbolic. So that is why the boundary action of water hyperbolic group is so important. So because you can get every information of water hyperbolic group from it's a boundary group boundary action. Okay. Okay. So far story is just a water hyperbolic group action on the hyperbolic space. So they are called geometry. Okay. So now extend water hyperbolic group action on non-positive curve space. So for example, some Kagel space. Okay, so this is also classical examples. Given by the Hitchin. So if you by using the irreducible embedding of PSL2R into PSL-NR, then you can get the surface group action on some space. Okay. So anyway, we have a surface group, the homomorphism in the PSL-NR. So then PSL-NR, the action, the space. For example, PSL-NR acts on the projective space or some symmetric space, so associated to the PSL, the NR. So that space is just you think of the quotient space, the PSL-NR quotient by the PSO, PSON. Okay, and the flag variety. So what is flag variety? Is the set of the all flag. So flag means that the ascending sequence of the vector space in Rn. So it's like this. So Hitchin actually studied the surface group action on the flag variety. And he found some stable the surface group action on the flag variety, so-called the Hitchin action. Okay, and also he proved that the Hitchin action form some connected component in the homomorphism space of surface in PSL-NR. So this is a kind of generalization of Heitman space. Okay, so any two case, the Hitchin result gives a Heitman space there. He generalized the Heitman space to the higher semi-simple regroups. Okay? Okay, and also, so this Hitchin, the space of Hitchin action is a homomorphic to Rn. This space is the higher the Heitman space. Okay, so this is also in an example which is stable, right? So it consists of the connected component. That means that if you perturb a little, then you again get the injective homomorphism. So can we understand that this phenomenon in terms of the convex group action? So this is people have tried to understand the Hitchin action by terminology of the co-convex group action, because but a little different, because the PSL2R acts on the H2, right, hyperbolic 2 plane, but the PSL-NR acts on this kind of thing. So all spaces are not the hyperbolic space, and also all these space do not have the hyperbolicity. Okay, kind of the Kagel space. So actually, this symmetric space associated to PSL-NR is a Kagel space. Okay, so totally, so yeah, depending on having the zero sectional curvature or not is a very different. Okay. So what is the difference between the PSL2C and SL3R? So this is example. So PSL2C is just an isometric group act on the hyperbolic 3 space. So it has some kind of hyperbolicity in group. But the PSL3R, this is the isometric group acting on the symmetric space. So this symmetric space having the non-positive sectional curvature. So it has the Euclidean 2 plane inside the symmetric space. Okay. Okay, so to understand the Hitchin action, we need to find some difference between the narrow curve, the geometry, space, and the non-positive curve space. Okay. Okay, so first trial. This is the trial to explain why hitching action is stable, okay, in the space of the group surface group action in PSNR. Actually, he hits the hitching give stability by using the Higgs boundary theory, but that is not. So I'm Jamir and Floridan. So their hitchings, the languages of cannot interpreted in the viewpoint of the geometry and topology. So geometer try to understand his theory. So in terms of some geometry or topology, so and so on. So this is a trial for that. Okay. So first, you try to just apply the definition of the convex co-compact group action to hitching action, right? Because the convexity gives stability. So people try to the convexity gives convexity gives stability of a hitching action or not. So but the answer is no. Okay. So Kent and the Kreiner Reeve, 2005. So they proved that. So actually, they gave the independent result. Okay. So suppose the gamma is a Zariski dance of the higher rank, simple regroups, then there is no proper closed gamma invariant, the convex offset of the associated symmetric space X. So that means that if you have some convex co-compact group action on the higher rank symmetric space, then the action is just the co-compact action. I mean the co-compact lattice or some kind of co-compact lattice of acting on some total geodesic subspace of the symmetric space. So that means that the convexity does not give any new phenomenon. Okay, and also it does not give some explanation for the hitching because the hitching action is a Zariski dance in PSNR. Okay. Okay, so next trial. So this is a successful story. The water hybrid group action on non-positive curved space. So first, the Rabori, the 2005, define the notion of the Anasov representation. I mean, Anasov group action. So by using some Anasov structure of hitching action. So he think of some bundle structure on surface by using the flag variety. And also he found some contracting, expanding property on the group action on the flag variety bundle over the surface. Okay. So anyway, he used some dynamics from the Anasov things. And also after that, the Fischer, the Binar, the expanded the Anasov structure of surface group action to the arbitrary water hyperbolic group. I mean from surface to the general water hyperbolic groups. So-called the Anasov group action, and then prove that the Anasov group action are stable. Okay. If you perturb a little the Anasov group action, then you again get injective homomorphism, and furthermore, that is also the Anasov group action. So in rank 1 symmetric space, so this is the symmetric space having negative sectional curvature, then the notion of Anasov group action coincide with the convex co-compact group action. Okay. This is quite a successful story. And here, as I told you, the expanding, some contracting, the property gives a stability of the Anasov group action. So that is a key key property explaining the stability. And also he elaborate interpreted the kitchen action. So in terms of some contracting, expanding the property on the black bright bundle over the surface. Okay, so here I just mentioned the analytical group action, what the analytical group action are. So this is the gamma, so must be the water hypergroup. Okay, so then G is a semi-simple regroup and X is the associated symmetric space. Then the group action is also if the orbit map. So you can think of the orbit map, right? The orbit map is a Morse code geodesic map. So in convex co-compact group action, we don't need a Morse. Okay, so we need a more stronger some the condition on the embedding this method. Okay, I'm not gonna explain what the Morse things, but so this is a more strong thing. And there exists some embedding this, okay? But the asymptotical embedding. So asymptotical embedding is involved with the contracting and the expanding property on the analytical group action. Okay, so anyway, the water hypergroup action is their dynamics on their boundary. So have played the essential role in defining the analytical group action and explaining the stability, their stability. Okay. Okay, so now let's move to non-hyperbolic group action. Okay, so far we first start with some water hypergroup and some negative some space, narrow sectional curvature space, right? But and then we replace the narrow curve geometry with non-positive curve geometry. So what's next? So let's extend this story to from the water hyperbolic group to the non-water hyperbolic. Okay, but this is not easy because, as I told you, for non-water hyperbolic group, it does not have a well-defined the boundary, or it has a totally different geometry from some negative curve geometry and so on. So this is a ongoing project in stability theory. Okay, so here is a simple example. So let the gamma be a co-compact lattice in higher rank semi-simple regroup. So then the gamma is not water hypergroup, as you know, because gamma acts on the Kajero space actually. So then if you think of H is another higher rank semi-simple regroup containing G, then the inclusion is rigid in H. So by Magritte superrigidity. So that means that this co-compact lattice in higher rank the semi-simple regroup is just a rigid. This is not. But we don't know this has a stability in some sense, okay? Because the rigid thing is also stable, right? Because around that inclusion, the homomorphism, there are no injective homomorphism, okay? Okay, so that means that one cannot find a non-rigid example in this way as the convex co-compact group action on H3. So then, what is the next idea? Then this is the next idea to study the non-water hyperbolic group, the action. Let's take the co-compact lattice in higher rank semi-simple regroup, the gamma, and embed into a larger group, okay? Like the diffeomorphism group of G mod P. So here, the P is the parabolic subgroup of G. So G mod P is, you can think of G mod P as some kind of the boundary of symmetric space. Okay, so this is just the boundary of symmetric space. Then the group, semi-simple Lie group, is embedded into this large group, right? So actually, the different group is too large. Then it is not rigid anymore because this different group is too large. So under this situation, then can we see the gamma action on this boundary is stable? If it is, then you can find some clue for the Kachero groups to be stable, right? So we try to figure out what happens in this situation. So there is some facts supporting this idea. The Sullivan proved that the water hypergroup gamma action on its boundary is stable in different mobility group. Okay, as I mentioned at the beginning of my talk. Okay, so that means that all sufficiently small perturbation of the gamma action on the boundary in different mobility group, then still the injected and preserve some dynamics. So this gives us some idea for studying the Kachero groups. Okay, stability. Okay, anyway, even if we know that this is stable, so we need to find some essential the feature of non-word hyperbolic group action, so which gives rise to the stability. Okay, so here's the main theorem. We proved that. So our question is answer to our question is yes. So if you embed the co-compact lattice of higher rank lattice into the different movement group boundary, then so this action is still stable in different movement group of the G-mod-P. Okay. So after our work, so the Cornell and Ram and so this group, Spatcher, 3 years later. So actually they are grouped in the GMOP program. Okay? So they are studying some discrete group action on the discrete group of the higher rank semi-simple Lie group action. Okay. So by using their technique in the GMOP program, they switch the diffeomorphism, the group to the homeomorphism. But if you embed into the larger group, the homeomorphism group, then so this action is semi-stable. Okay? It is not stable. So actually, the almost stable. Okay? But so there, the approach is too different from our approach. So our approach is just the geometric group theory. Okay, let's back to the Sullivan's idea to explain why this kind of thing happens. Okay, the Sullivan introduced the notion of the hyperbolic action. Okay. Having some expanding and unparalleled traveling the property. So by using the viewpoint of dynamics and the geometric group theory, by using this technique, he can prove that the convex co-compact group action is stable in diffeomorphism. Okay, diffeomorphism group of S2. So what is the hyperbolic group action? So he defined the hyperbolic group action as follows. So first, red M is a compact C1 manifold, and the gamma, the group, finite engineering group acting on M by diffeomorphism. Then, and the lambda is the gamma invariant of the compact subset of M. Okay, this is exactly the same situation of convex co-compactness. So then the action is said to be hyperbolic if the action is expanding. Okay, I will give you what is the action is expanding. And all delta ray for each x are the M fellow traveling. So he used two properties, so expanding and M fellow traveling property. By using two notions, he defined the hyperbolic action. Okay. So what is expanding? So the gamma action on lambda is expanding. That means that you can, for any x in lambda, then you can find some expanding generator around a point. Okay. So there is a definition of the expanding action. So there exists some finite symmetric the generating set S and associated the open set. This is actually the expanding domain for the S1 inverse. Okay, so S1 each SI inverse is expanding lambda expanding on the UI like this, and also you can cover the lambda. So gamma invariant complex subset lambda is covered by this open set. So this is a definition of the expanding. And then before giving what is the M-fellow traveling, so if you have an expanding action, then you can get some notion of the encoding each point in lambda. Like this. So if you have the open cover, then choose the Riemann number. Okay. So after that, so we define some one operation. So what is the one operation on the points on the lambda? So if you choose x some on lambda, then so think of the delta ball centered at the point x. So then delta ball is contained in some point, some open cover, right? Because we choose delta as the Riemann number. So one of that. Okay. So then the delta ball around the center of the x is contained in some, just to say U1. Okay. Then U1 is S1 inverse the expanding lambda expanding the domain. Okay. So then by using the S1 inverse, we move with the x to another point by the action of the S1 inverse. Okay. So by using this operation, if you start with a point x, first choose a point x. Then by using this operation, then you can get a sequence of points on lambda. Okay, and also sequence of the generators, right? The expanding at each step. And also you can define some array. So this is we want to prove back the all points to x. Okay, starting point. Then by using this sequence. So usually you see that this maps each xn plus 1 to x, and also this is backward, right? We first the x maps to by using some expanding the elements generator. So the back way, then you can get some contracting things. Okay, so this explains how this element contracting around the xn plus 1. Okay, so. And also, this is you can think of the sequence of domain like this. So this contains this domain contains x, and also actually, so this is a nested domain. Okay, so exponentially the shrinking sequence of domain. Okay, So, and their intersection consists of just one point, x. So this is trivial. So this is starting the situation. Okay. So this, you can do this if you have the expanding action. Okay. Okay. Then what is the unparalleled traveling? So unparalleled traveling is okay. So you can find a sequence, right? But there are many choices for each step. Okay. So that means that there are for each x there are many infinite. Actually, the infinite many. The code is we call this is array and this is code. Infinite many the code, okay, for each x. So there is some canonical some code for each x. So we need to control the set of all the code, okay, by using the unparalleled traveling property. So what is the unparalleled traveling property? So two rays for the fixed point x are the unparalleled traveling. That means that the Hausdorff distance between them are uniformly bounded by the n. Okay, so they are they are not infinite away from each other. Okay. Okay, so then so then you can understand what is a hyperbolic action. Okay? So first expanding, and for each x, all delta ray satisfying the unparalleled traveling property. Okay. So then you can prove the stability of hyperbolic action. So this is a sketch of the proof of stability of hyperbolic action given by the Sullivan. So if you have a hyperbolic action, so this is expanding, then gives some delta rays for x, each point x. Then, so you have some exponentially shrinking the nested the sequence of domain, whose the intersection consists of just a point x. Okay. After that, we perturb this action. Okay. So we perturb a little this action, then we can assume that the perturbed action is still expanding, because expanding the property is an open condition. So every the perturbed ray also, so that means that if you perturb the original action, then gamma is changing to another elements. But it's the contracting property on each delta ball is preserved, okay? Because the perturbed the gamma action is still expanding. So then you have also exponentially shrinking nested sequence of domain by using this data. Okay? Then this gives us some point, because this is exponentially shrinking nested sequence of domain. So their intersection gives us just a point. So we define this point by some PR per x. Okay, so this is defined by a code alpha for x. Okay, but this unparalleled traveling property gives the well-definedness of the PR per x. So that means that if PR per x is independent of the choice of the code alpha. Okay, so even though there are infinitely many codes or lay for each x, but we don't care about the infinities. So every ray gives just the same point. Okay, so that is key, the idea. And also by using this, you can define the gamma equivalent, the injective continuous map, from the lambda to the m. And also this is actually the homomorphism onto its image. And by using this, you can prove that the perturbed action is still injective. Okay. Okay, so this is what Sullivan proved. So. And also, after he proved the stability of hyperbolic action defined by himself, he proved that the convex co-convex group action on their limit sets are hyperbolic action, okay? In the sense of Sullivan. So the convex co-convex group action on their limit set are stable in different groups. Okay? So how to prove this one? So this one is can be proved easily by using some geometry, the property on the hyperbolic space. So like this. So first, you can see that all delta ray are some uniformly cogeodesic in calligram. Okay, this is just a. We don't care about the space. So this property is always true for given the hyperbolic action. But by using the Morse lemma, so what is Morse lemma in delta hyperbolic space? So there is a Morse lemma in delta hyperbolic space. So the uniformly cogeodesic in delta hyperbolic space with the same endpoint, then there are the end fellow traveling. Okay, so this is the powerful lemma in the delta hyperbolic space. So by using the Morse lemma, because the convex co-convex group is a delta hyperbolic, so by using the Morse lemma, you can prove easily the end-fellow traveling, the property of the convex co-convex group action. The expanding action is trivial, so you can easily see that the convex co-convex group action on their limit set are expanding, and by the Morse lemma, the end-fellow traveling property follows. Okay, so there is the proof of the Sullivan for the compact group action to be the hyperbolic action. Okay. Okay, so here the further application to water hyperbolic groups actually is the Sullivan stop here. Okay, and also there is a little gap in his paper, but we try to fill in the gap, and we want to extend his idea to the non-water hyperbolic group action. Okay, so you can apply to this situation. So every water hyperbolic group action on its growth boundary is a hyperbolic. So in the sense of the Sullivan, that means that the water hyperbolic group action on its boundary is stable in diffeomorphism of the boundary. Okay, but the 2022, the Mann and Manning, the Weissman also he dropped the diffeomorphism. So they proved that the action, the boundary action of the water hyperbolic group is semi-stable. So in homeomorphism group, but there are big difference between the diffeomorphism group and the homeomorphism. Okay, because the diffeomorphism group you can control some expanding factor, contracting factor, and so on. But in diffeomorphism group there are no notion of the contracting or the expanding. So, but their idea comes from the Sullivan. Actually, they found some kind of the expanding domain. Okay, in the setting of the C0 setting. Okay, so what is the problem? His idea. Extending to the non-word hyperbolic group actions. So this picture gives one simple reason why the non-water hyperbolic group action is so difficult to deal with. So this is a cogeodesic in the Euclidean to space. Okay. In that hyperbolic space, the quasi-geodesics gives just 1 point. That means that every quasi-geodesic in that hyperbolic space define some one direction. Okay. But non-water hyperbolic case, it does not true anymore. So this is the extreme case. So the spider defines the whole direction. Okay, so this is not good example. So, but to deal with the Kajero space, you have to control this kind of thing. Okay, so we define the new notion. I mean, by the weakening the M-parallel traveling the property to the so-called the mindering hyperbolicity. So we define some mindering hyperbolicity in like this. Actually, what is what is this picture? Okay. Actually, think of the co-compact lattice action on the higher rank symmetric space. Okay. So then the higher rank symmetric space, the co-compact action is expanding. So you can prove this easily because you have a co-compact action on the higher rank symmetric space, then you can get some sequence of the compact set toward some some boundary point. Then that sequence gives us some expanding the property. Then if you have so the co-compact lattice action on the boundary in higher rank case, the expanding. So then we can encode the all points on the boundary, right? So we have all the ray. Then the ray turns out to looks like this, okay? In hyperbolic case, so this kind of thing does not happen because it satisfies the M-parallel traveling property. So they only gives just one direction. But in higher rank, it does not define just one direction. They have a lot of direction. Okay. So for example, like this. So here, we can see the many direction, right? But we can find some another so this is geodesic ray in higher rank symmetric space. Then you can find the red thing. So this is also the quasi-geodesic ray. So and also by interpolating these two rays via some red thing, so we can see that the M-parallel traveling property can be replaced with some weakened condition. Okay. So this is a definition, but this definition explained so this one. Okay. So anyway, we define the mindering hyperbolic group action because this is a kind of mindering, right? So we think that the mindering is the best term explaining this action. Okay, so the action is expanding, and so we say that it's delta equivalent. That means that it satisfies this picture. Okay. So then, we prove that if you have the mindering hyperbolic group action, then this action is unstable. Okay. So perturb a little, then still have an injective representation. But this is a very good the notion for studying the Kajero space action. So because we proved that the co-compact lattice in semi-spherical regroup that its action on the boundary is a mindering hyperbolic group action. So that means that this is, even if this is the co-compact lattice in higher rank is rigid in semi-simple regroup, but so this is stable in the diffeomorphism group. Okay, so actually we deal with some Lipschitz homeomorphism group, but you just think of the diffeomorphism. So that means that usually the people think that the co-compact lattice in higher rank does not have any hyperbolicity, right, as delta hyperbolic groups. But we've figured out the why. So this is stable because the co-compact lattice in higher rank have a kind of mindering hyperbolicity. Okay. And this is another application. So the convex, the projective space. So this is the projective torus. Okay, if you define a AB like this, then it stabilizes this triangle, and so this group acts on the torus, the group action. Okay, so it turns out that this action is a mindering hyperbolic. So the projective space, projective group, convex projective manifold is also one of the good examples in studying the Kessler group space. So we try to how to understand the convex projective group action in terms of the mindering hyperbolic, the group action. Okay, so here is the further study. So there are some Kessler. So this is just a conjecture, and the real projective space. So okay, yeah, I stop here.
Okay, let's thank the speaker. Is there any questions? Okay, so I have a question. So like in your title, you mentioned like the cat zero group action. So what does cat zero mean?
Cat zero means that if you that is some kind of generalization of the non-positively curved space. So if you draw some triangle, then the similar to the delta hypothesis.
So is cat zero means some classification of space or
Yeah.
or the classification of groups because it's
Chris. So if the group acts on co-compactly on Kessler space, then we call the group Kessler group.
So and is there any generalization like cat one? Like what does the zero mean?
Zero is just you think of the sectional curvature.
So so you curvature is zero.
Yeah.
So only zero makes sense.
Yeah.
I cannot say 1, 2.
Yeah. That is the just a simple way to understand the number. Yeah, cat 0, cat 1, yeah, cat -1.
I see. Is there any other?
Where does the name come from?
Cat. I don't know actually. I don't know. Actually, I'm not the geometric group. I'm not studying. As I told you, I studied some symmetric spaces, so I saw. But so this technique, so we shall recommend so this kind of technique to the geometry group theory. So we first, I start to study the Kessler, the group, the Kessler space as well.
Okay, is there any other questions? I have further questions. So you just mentioned that the curvature is 0, right? But in your slides, you mentioned a lot like the hyperbolic curvature. So that means the curvature is negative, right? So, what I mean, is that related or? Is it what? So in your slides, you actually say it's a hyperbolic thing. That means negative curvature, right? And then your title is like 0 curvature.
So because think of the PSL 3R.
Yeah.
PSL 3R.
Okay.
Then so think of the PSL 3R quotient by the PSO 3.
Okay.
So this is a symmetric space.
Yes.
So it has a curvature 0.
Yes.
So the Euclidean, the two plane is embedded into the symmetric space.
Yeah.
So that is a cat zero space.
Yeah, but actually, but you use you mentioned a lot like negative curvature. So how does the theory in the negative curvature apply to the zero curvature case?
So we cannot apply some negative curvature the property to the directly to the visual space. So so that is why we define some mindering the thing. I mean okay, so this thing. Okay. So this is just is not phenomenon in the negative curvature space.
Okay.
This is exactly what happens in the vector space.
So the most important thing is the curvature zero instead of.
Right. So curvature zero so makes a problem.
I see, but
Yeah.
curvature negative is easy, right?
Yeah, it is easy.
Yeah. So do you think curvature zero as a limit of the curvature negative curvature?
Yeah.
So you do okay. Okay, thank you.
Yeah.
Okay, is there any other questions?
In the very beginning, we talked about the group homomorphism, row and row can be closed.
Yeah.
What do you mean by that?
Okay, so if you start with the topological group G, so and gamma is just the abstract group. Okay, so the finite generate the group, then you fix some finite generators, and then you can think of the space of all homomorphisms, right, of gamma into G. Then you can compare some generator. So if you actually you can define the compact open topology in the space of all the homomorphisms of gamma into the topological group G by using choosing some generators.
So there is no metric in this.
No. So but there is a topology on the group G. So if you have some representation, then there is some image of generator, right? You draw some small neighborhood of each, and the generator, the perturbed generator, the state in that neighborhood, then you can say that the two representations are close to each other.
Small neighborhood.
Yeah, small neighborhood. Just small neighborhood. Yeah.
I mean, there's no metric. How do you define small?
I mean, if you have a element in G, group G, a topological group G, then you can have some open neighborhood of G, right? So that gives some closeness. I mean, so this is just a vague just the argument to topologize the space of homomorphism. So gamma into G.
So by enclosed, you just mean they're in the same neighborhood.
Right. Yeah. Right.
Okay. Is there any other questions? If not, let's thank the speaker again and.